So moving on to our application problems, we're going to look at applications of exponential growth and decay. So what we're going to have is we're going to have a function that's in terms of t, which is t is usually going to be a time for us because we're talking about growth and decay. So f of t equals a sum naught e to the kt, or as we're probably going to write it most of the time, is a equals the a sub 0 e to the kt. So when we write our equations, it's a function in terms of t. So we expect t usually when we're trying to write a model is going to stay t. Everything else is going to be filled in with something. So a sub naught represents your initial amount. A is your current or future amount. So somebody's called that future value. K is going to be your growth or decay rate. And it's going to be as a decimal. And then t is just going to be time. So whatever unit of time we have. So if our k is positive, then what we have is our function is going to model a growth. The function models the amount or size of a growing entity. A sub 0 is going to be the original amount, and or the quantity at time 0, and a is going to be the amount at time t, and k is going to be a constant representing a growth rate. So k is a growth rate. Now, if k is less than 0, so negative, then the function is going to model a decay of our entity. A sum naught is still going to be the original amount at time 0, and a is going to be the amount at time t, and k is going to represent a decay rate. So if k is negative, we have decay and a decay rate. If a is positive, we have growth and a growing rate, or growth rate. Now here, we got a sub 0 e to the kt. If k is positive, then we should see a exponential equation that's growing, so we get exponential growth. If our k is negative, we should be having something that's decreasing, so we're having exponential decay. So we're going to start working on some application problems. So in the year 2000, the population of Africa will be 108 million, and in 2020, it has grown to 1,341 million, or 1,341,000,000. We want to use the exponential growth model A equals A sum naught e to the kt, in which k is the number of years after 2000. So when we make a growth model, we want to know what k is, and we want to know what e sub 0 is, because we want to make a model that I'm going to put a time t in, and I'm going to get a population A. So we want to find the exponential growth function that models this data. So I'm going to give myself a little extra, space here. Let's do that in white. Okay. So what we know. We know that the initial population is 807. We won't worry about putting the billion there. We just know it's what's supposed to be. And A is going to be 1,341. We know T is time after 2000. So we're in, when we get my 1,341, then T had to be 20 years after 2000. So the only thing I don't know is K. I have an A naught, I don't have a K, but I have the information to find K. Because I know 1,341, it should equal 807 E to the K, which I don't know, 20. So what we have is an exponential equation. We need to find K so that we can solve this. So we have to isolate the exponential. So we're going to have 1,341 divided by 807. That's going to equal e to the 20k. Now, if I do a natural log of both sides, remember that if I do a natural log of e to a power of b, then b is just going to be left behind. So we're going to do natural log of both sides, so natural log of e of 20k. So what we're going to have is natural log of 1,341 divided by 807 is going to be equal to 20k, which means if I want k, that's just natural log of 1,341 divided by 807, all that divided by 20. So I have not tried to find my natural log of anything because I'm waiting to keep it to the very end to avoid rounding errors. So what I get here is that k is going to be equal to 0.0, and we're going to round it, let's just do 4 decimal places, to 254. That's going to be my k. So my model of population of Africa, T years after 2000 is going to be, so we want to leave the A empty because we want to just generate whatever population we're getting. A naught is still the 807. E, now we know K is 0.0254, and then we're going to leave T empty because we want to be able to put any time in. So I can find the population at any time using that model. Okay. Let me write that down again. So our model was A is equal to 807 e to the 0.0254 t. So by which year will the population reach 2,000 million or 2 billion? So if I want to find that out, it's not much different than the problem I did last time. What I have here is that I know that I want to know what the population when it reaches, there we go. Sorry, I got something in my way here. 2,000. So 2,000 equals 107 e to the 0.0254 t. So I want to get t by itself. So it means I have to isolate the exponential. So that is just 2,000 divided by 807, which equals e to the 0.0254 t. So now if we do a natural log of both sides, natural log of 2,807 equals natural log of e to the 0.0254 t, which is natural log to 2,000 divided by 807 equals e to the 0. Oh, sorry, we don't need the e anymore. So remember what gets left behind is just that exponent, so 0.0254 t. So actually we could get to a point, eventually we're just going to kind of skip this step and go from here to here. So t is just natural log 2,000 divided by 807, all of that divided by 0.0254. Second, I was trying to find my answer on here. So we have, I have to do it one more time, natural log of 2,000 divided by 0.7 divided by 0.00254. So we're going to get 35.73 years. So if I'm at 35, I haven't quite reached 2 billion. So I'm going to just round it up and say 36 years. So the question is, In which year will the population reach 2000? So remember, we started in 2000. This is 36 years later. So the year is actually 2036. The population of Africa will reach a population, will reach, sorry, where is the population? The population of Africa will reach 2,000 million in 2036. Okay, so for you, an artifact originally has 16 grams of carbon-14 present. The decay model A equals 16 e to the negative 0.000121t describes the amount of carbon-14 present after t years. Use the model to determine how many grams of carbon-14 will be present in 9,507. Okay, so this one was actually a really easy one because the only thing that we have here is we know what T is. So we don't have to do a bunch of math here. We just need to figure out what's going to happen when year T is 9,507. Then we'll give you a much harder problem. So that is 16 e to the, so I'd use parentheses or brackets or something along the entire top here. Negative 0.000121 times 9507. Oops, just a second. That did not go into my exponent for me when I did that. Negative 0.000121 times 9507. Okay. So we expect to have only 5.06 grams present. So we actually use carbon-14 to help us age items. So I went backwards. So here, an artifact originally has 23 grams of carbon-14 present. The decay model A equals 23 e to the negative 0.000212 t describes the amount of carbon-14 present after t years. How long until only 2 grams of carbon-14 are present? So this is a little more closer to what we do. So we usually have an idea of how much carbon should be in an object when it is first created, because we expect, like when they cut down something like a tree, that the tree is instantly turned into something, so we know about how much carbon a tree should have, or a particular kind of tree. And so we can use it to kind of grade an item, figure out how old an item is. So we're just trying to figure out how old this item is. So we're really just asking how old is the artifact. So we know that in the end that we expect it to only be 2 grams. So what we mean to find here is T. How long has it been sitting there? So we need to isolate the E. So we're going to do 2 divided by 23 equals E to the negative 0.000121 T. Now, if we do a natural log of both sides, a natural log of 2 over 23 is going to be equal to, so remember, if I do the natural log, all I'm left with is the exponent here, because it's already a base E, so negative 0.000121 T. So T is just natural log of 2 divided by 23 divided by negative 0.000121. So that negative is important because it's not there. It's going to just a wrong answer. So we need natural log of 2 divided by 23, which is going to be negative itself. So when we divide by a negative, we should get a final answer that is positive. So we get T is, so we expect the item to be 20,000 years old. So we're going to round up to this. So we expect this item is about 20,185 years old. And that is how we carbon date. So we have some common problems that use exponential growth or decay. So for decay, we talk about half-life frequently. So half-life is the time it takes for a radioactive isotope to decrease to half of its initial quantity. So if we have A to the A sum naught E to the KT represents the decay of the element, then the half-life of the element is going to be 1/2 of A naught equals A naught E to the KT, which means that 1/2 equals E to the KT. So if I do a natural log of 1/2 equals KT. So T is just natural log of 1/2 divided by K. Also, K is just the natural log of 0.5 divided by T. So we can kind of use this relationship to avoid doing a lot of work for us and just use this part right here or right here to either figure out what the decay rate is, or in this case, find out what the half-life is. So remember, this only works half-life problems. So the formula for the decay of radium is A is equal to A sum naught E to the negative 0.000433 T, where T is in years. We want to know, what is the half-life of radium? Well, like we saw before, that if I want half-life is just the natural log of 1/2 divided by K. So natural log of 0.5 divided by negative 0.000433. Remember, because this is my K. So if we just do a natural log of 0.5 or 1/2 and divide it by negative 0.000433, we get, remember this is in years, 1,600.8 years. Okay. So when I looked it up, radium's half-life is just 1,600 years. So there was a little rounding in this problem here, but we're pretty close to what it is. So your question is the formula for the half-life of iodine 131, which is radioactive, is A equals A sub 0 E to the negative 0.0862 T, where T is in days. What is the half-life of iodine 131? So like we said, if we want to find half-life, is just going to be natural log of 0.5 divided by K. So here my K is a negative 0.086. So natural log of 0.5 divided by negative 0.0862. I think I mixed the 0.2 last time. So we are going to have 862. And so we're going to get 8.04. And we said this is in days. And so when I looked this one up, it was just actually just 8 days. So we're rounding our decay rates. So our decay rates are not coming out necessarily exactly. And it's probably not exactly 8 days anyway. Like all this, remember, it's just rounding. So this is something that decays very, very quickly compared to radium, which decays very, very slowly. So worksheet 4, so the half-life of strontium-90, which I believe replaces calcium in your bones sometimes, is 28 years, meaning that after 28 years, a given amount of the substance will be decayed to half of the original amount. Find the exponential decay model for strontium-90. So remember, half-life is equal to the natural log of 0.5 divided by K. So if we wanted K is just the natural log of 0.5 divided by the half-life. Or last time we used T for this. So we have a half-life of 28 years. So my decay rate on the exponential decay model. Okay, so I need the decay rate for my decay model. This is going to be natural log of 0.5 divided by 28, which is going to give me a negative 0.2548. We'll do it there. So my decay model is A equals A sum naught, because we don't have an original amount, E to the K, which is negative 0.0248 T. And once again, you could always check this one out just to see if it works. So let's see, if I have 100, I'm not sure how to measure that, 100 strontium atoms, let's say that, 100 of them, how many do I expect to have left over? After 28 years, we're going to see if we actually get 50 left back. So we're going to have a negative 0.02548 times 28, which is going to give me approximately 59.9. So yeah, about half of it's left over. So our model is correct. We do have the right decay rate. So we also have doubling time, which is another exponential model that we talk about frequently. So doubling time is the time required for a quantity to double. So usually this is used in cases of looking at investments, how long for an investment to double, or sometimes how long it takes a population to double, something that has an exponential model to it. So A equals A sub 0 e to the kt. If we want doubling time, that means we're doubling A naught. So 2A naught is equal to A naught, or A sub 0 e to the kt, which means that we're just going to have 2 is equal to the ekt, which means natural log of 2. That was a mistake in there. Natural log of 2 equals kt, which means t equals natural log of k. Which then, like I said, you can get that around, get your doubling time as well. So this is going to tell you doubling time. And we can use it backwards to get our decay, our growth rate. So for an example, if we had $2,000 is invested in an account with an annual interest rate of 2.3% compounded continuously, how many years will it be until the account balance doubles? So this is a formula we've seen before. So we are starting with a principal of $2,000. We have E, and our rate is going to be 0.023 to the T. So we want to know how many years is it going to take for our account to double. So double time, or doubling time, is equal to natural log of 2 divided by K. So this would still be my K, even though here I use that. So it's part on the T. So natural log of 2 equals 0.023. So log of, oops, I accidentally put sine function here. Log of 2 divided by 0.023 is going to be 30.14 years, or approximately 30 years. Which is why they suggest when you invest money, and start investing really early if you can for your retirement, because it's going to take that much time for your money to double. So for our last bit here, so sometimes we have something that's not written in base as a base e, but another kind of base. So if y equals a to the base b of x is equivalent to y equals a to the e of the natural log of b of x. So the reason we could say that is because if I have e to the ln b, well, that just equals b. So a to the natural log of ln b to the x is just a to the b of x, which is what we have right here. So, which we're actually working it backwards. So if I'm going to rewrite y equals 4 to the 7.8 x in terms of base e, remember y to the b to the x is now going to be, or a b to the x is now going to be y equals a to the e natural log of b to the x. So we just write y equals 4 to the e to the 7.8, oh, sorry, natural log, 7.8 x. So the only thing we want to change is this. What is natural log of 7.8? So we're going to round to 3 decimal places. So this is going to be 2.054 x. So that is the way to convert it. So our very last problem is now rewrite y equals 33 0.5x in terms of base e and express your answer in terms of a natural logarithm rounded to 3 decimal places. All right, so y equals 33 0.5 to the x. We're going to just change that to 33 e to the natural log of 0.5 to the x, which is going to be 33 to e to the, so we just need a natural log of 0.5, which is going to be a negative 0.693 x. So as you see, we had a decay rate because we got that 0.5, so we see that's going to change to that decay rate right there.